gives me great pleasure now to introduce our keynote speaker, Mr. Iain Wight. Iain is the Business Development Director of Williams Advanced Engineering and is going to give us an insight into the world of advanced engineering from his point of view.
Thank you. Thank you very much for inviting me. My name is Iain Wight. I'm the Business Development Director at Williams Advanced Engineering. What I wanted to do today was to give you a little bit of an insight as to the journey that we've gone through over the last 7 years or so. Now, we've seen a lot of changes in our industry, and we've taken a move from a Formula One team into an advanced engineering team. But when you couple the number of disruptors that we're seeing in the motorsport and the automotive market, this is quite huge just now, and quite a lot of change is happening. Now, I think in your industry you're seeing a lot of change as well. There's a lot of new technologies coming in. So hopefully some of the things I can discuss today will be relevant or insightful to the areas that you're working in. Now, Williams as a group, we were formed in 1977, so we're 41 years old now. Primarily known for our Formula One team. We've been very successful in the past in Formula One. We've won 16 World Championships. It is a very, very competitive world, as I think last weekend probably showed. It was a pretty tough weekend for us. We have around about 950 people actually on site now, of which 250 are in the Advanced Engineering Group, and the rest are focused on getting 2 cars to the grid every 2 weeks through the summer for the Formula One races. Now, as you can imagine, we have quite a lot of competencies within our group to get state-of-the-art Formula One car onto the grid. Our facilities are pretty much second to none. We have 2 wind tunnels on site, 100% wind tunnel, moving floors, moving walls, really absolutely state-of-the-art. 150% tunnel that's a little bit older now, but we still use it for a number of things. We have a lot of capability in CFD, in analysis, in tools where we analyze thermodynamics, aerodynamics, simulation, any kind of dynamics, kinematics within the vehicle itself. We have quite a large machine shop, composites manufacturing, prototype and test area, and assembly areas. So really we have a lot of capability. But if you follow Formula One, you will know that a lot of the regulations have changed over the last few years. So while we have 2 wind tunnels, we can only use it for Formula One for maybe 1 week, 1 tunnel per month, which isn't a lot really. So that gives us a lot of capability and capacity that we can deploy into other areas. It's the same with CFD analysis. We are constrained by how much we can use in regulation. So it enables us to employ this into other areas really. So as a result, we've taken these core competencies that we have and deployed them into other areas. Now, we formed at Williams Advanced Engineering in 2010. The reason for forming it really was we were approached by Jaguar Land Rover to develop this car. As ever, the car had some fairly tight targets. At the time, they wanted the performance of the Bugatti Veyron, they wanted the electric range of the Chevrolet Volt, and they wanted the emissions performance of the Prius, all in one vehicle. So a few challenges really for us. We put a team together of about 60 people. Jaguar did the styling. I think the car is pretty immense. If you've seen the Bond film, then you've probably seen the car. It had a 1.6 litre IC engine in it, putting out around about 500 horsepower, which was turbocharged and supercharged. We had 2 electric motors in it, one in the front, one in the back, about 200 horsepower each, to give full 900 horsepower 4-wheel drive, capable of running in electric mode, in hybrid mode, or an IC engine, or an IC only, or with everything together. Now, unfortunately, Jaguar didn't want to take the car forward into production, which was a shame because it was a very good car. We developed it incredibly quickly. We had the first prototype, fully trimmed prototype, running 12 months after starting from a clean sheet of paper, and we were close to being production ready 18 months after the start. So very, very short development times. Jaguar decided not to go forward because there's quite a lot of competition in the marketplace in this area. Porsche just brought out the 918. Jaguar had a lot of car platforms they were running with. This was another one into an area that they weren't quite sure about. It's in the kind of 700,000 to £1 million price tag car, so a little bit away from where they normally are. But that left us with a dilemma. What do we do at this point? We've got a group of very competent guys. We've pulled a lot of them from Formula One. We've pulled people in from the automotive industry. How do we go forward? What do we do? We took the decision at that point to actually move forward and see if we could win some programs based upon the capability that we thought that we had. When we looked at what we had, we knew that we had a lot of technology creation from the Formula One side. We knew that we could commercialise this, and then we could apply it to what customers want, not just in the motorsport or automotive sector, but across a number of different sectors. I've always thought it's a little bit of a waste that so many people are employed in Formula One. They create so much technology, and yet it's only focused on getting these two cars to the grid and going faster around the circuit. So the opportunity to employ this into different areas it's quite an exciting challenge for us, really. Now, the first thing that we looked at doing was moving into the automotive market. So we had to really define a set of rules as to what we do, how we do this. So we set out a number of things. Basically, we had to make sure that the capability that we had was aligned to the target sectors. No point in taking something that people don't want into a sector. We wanted to invest from the Formula One base and move that forward. We tried to maintain a focus that have the roots in motorsport, expand the low volume manufacturing capability that we have, and while we have very, very good quality control, you can see that from any Formula One team now and the reliability that you see in Formula One, we don't have the accreditation standards, so we needed to go through that process to prove to the outside world that actually, while we have good quality control, we need to prove it. But the biggest thing that we took with us was the can-do attitude, the responsiveness, the agility, innovation, and the passion that you see within motorsport, and then apply it into other areas. Now, that took with us a number of areas I think we're fairly specialist in, that you can either apply into a complete solution, or you can take bits of it. So, in lightweight materials and technology, we are experts in carbon composites and metallic parts and combinations of the two. Since 2009, when hybrid power was introduced to Formula One, we have become experts in mechanical hybrids and battery and energy storage systems with very, very high rates of charge, very high rates of energy deployment. You've probably seen in the last few years the automotive industry has been very heavily become electrified. This has meant that the technology that we've had has been very relevant in these areas. Aerodynamics, very strong for us obviously. And the key for efficiency is becoming more and more relevant to the automotive manufacturers. Couple that with driving dynamics and low volume operations, and actually you've got quite a nice package really that becomes sellable. The market drivers that we see are not too different to any other area of transportation, and certainly a lot of the other industries that we see. Everybody's driving towards lowering emissions, zero emissions, reducing a carbon footprint, dealing with autonomy, so taking the human out of it. We've touched on that a couple of times this morning, and dealing with big data. So when you're hit with a lot of data, how do you use that to the best endeavours? How do you get the relevant information out of that? We've been doing that in motor racing since probably the early 80s through telemetry and data logging. Taking data from the car, using it to make it go faster. That's put our technology drivers into fairly obvious areas really. Electrification, lightweight structures, autonomy and energy systems. Now, to give you a little bit of an example of some of the things that we've done, I've picked a few case studies focused around three main areas of competence, I think. So, aerodynamics, energy systems, and lightweight structures. Pick the example on the left, the blade glider. We were asked to do this around about 3 or 4 years ago by Nissan. It was at a time before electric vehicles were quite so popular and prevalent. We were asked to try and make an electric vehicle fun. Because there was the Nissan Leaf at the time, there was things that the cars weren't overly dynamic, they weren't perceived as fun. Nissan wanted to also demonstrate the narrow track front end that they had on the vehicle for improving aerodynamics. So we developed a full wind tunnel model for this, we developed a complete ground-up car, put in a full electric vehicle powertrain into it. We ran with 2 electric motors on the rear and completely separate powertrains. Developed a torque vectoring system so that actually when you got in the car you could drive it in a very safe mode, very comfortable handling, or if you wanted to be a complete hooligan, you could wind the dial on the steering wheel and get it sideways through every corner, and quite a lot of safety as well. All governed by the control system on the vehicle. Now that car's, well, we made 2 of them, they've been touring the world really on tour. If you go onto Google, there's quite a lot of write-ups on it, so you can see it running. The one on the right, touched on earlier, CX-75. It was quite an aerodynamic and thermodynamic challenge for us, because the vehicle had 9 separate cooling systems in it to cope with the IC engine, the battery systems, transmission, and the electric drive systems. Packaging that into a beautiful and efficient body style was quite a challenge actually. Involved a lot of CFD work and an awful lot of aerodynamic work to make sure that the blend of performance was correct. The example in the middle is completely different again. It's a complete different sector, and it shows what you can do if you take technology from one of your core areas and apply it to a problem that an area has. If you look at the grocery industry in the UK, if you go into a supermarket and walk through the chiller aisle, you know, well I know, my wife knows, she hates it, that when you walk through the chiller aisle it's freezing because the cold air spills out. I for one, I've got quite frustrated at this in the past because you spend all the time heating up the air in the store, then you cool it down. It's quite disrupting when you're shopping, but it's the way that things have been for a long time now in the supermarket industry. People don't like doors. Doors are open and closed, they break, they create a barrier to sale, so they're not a popular choice for supermarkets. So how do we make these more efficient? Very simple really. You put an aerodynamic device on the front of the shelf, so that when the cold air drops from the top, it is turned at each shelf back in on itself to keep the gap between the cold air curtain and the ambient air and avoid spillage. Very, very simple. And you kind of think, well, it's kind of clever, but so what? You know, what does that do for me, really? The grocery industry in the UK uses about 10% of the UK's gross energy. We trialled this with Sainsbury, who are about 10% of that industry. So Sainsbury's use 1% of the UK's gross energy level. The chiller units and refrigeration in the supermarket accounts for about half their energy usage. We saved around about 30% of the energy on a chiller cabinet. So that, from a little bit of extruded aluminium, is actually making quite an impact to the UK's energy industry. Very, very simple, can be retrofitted. So now we have it run out pretty much in all the Sainsbury's stores. Asda, Marks and Spencer's, Waitrose, and most of the other big supermarkets are following. So slightly different way of working, slightly different way of applying aerodynamics to an area. Electrification. 2 examples here. Aston Martin. Aston Martin are renowned for big engines, high performance, a lot of noise, a lot of theatre with their cars, really. And I love them, you know. When one passes me, I wind the window down, I like listening to them. But they also need to stay relevant within their industry. They were very keen to develop an electric vehicle, show it to the investors, show it to the board, to gain approval to take it into production for the future. We converted this vehicle, which was a V12 Rapide, to an electric powertrain in a 9-week period. So we took out the full powertrain, put in an electric vehicle powertrain. It was a bit scary timing. We used existing parts that we had around us, but it enabled Aston Martin to demonstrate a full electric powertrain with the handling dynamics that were appropriate for the vehicle, to their investors and to their board. This is now going forward into production and will hit production soon. We're working with them to develop the systems on it, so hopefully it will allow Aston Martin to move forward with technology and help them stay very relevant within the industry. Car on the right, that's actually about to hit the forecourt now. That's the Jaguar I-Pace. We developed the first concept car for that. That was taken to Geneva show last year. Then on to a completely different example in the middle here. Got some nice kind of high performance vehicles. Now we have a Brompton folding bike. If you're familiar with bikes and Bromptons, they have quite a cult classic status, very, very popular in London. They wanted to put an e-motor onto their bike, but very constrained on packaging because of the way that the bike folds up. We worked with them. We identified the front hub as being probably the best place to put a motor. We then developed a motor with exactly the same technology that we used for our Formula One cars motor that we developed, packaged an inverter, packaged a planetary gear set in it, went through the prototyping stage, worked with the manufacturer in Taiwan to take it into production, and developed probably one of the highest power density e-motors that is in the bike industry just now. If you can imagine, it's packaged into a 20-inch wheel at the front with the ability to use standard spoke lengths to get it through a production environment. Quite an interesting job for us, really. And then some examples of lightweighting. The example in the middle is kind of business as usual for us. We were approached by Nissan. They wanted to get the lap record at the Nürburgring Nordschleife with their GTR. We redid the handling, redid the aerodynamics slightly, and took a lot of weight out of the vehicle, enabled them to turn up at the track, knock 30 seconds off the lap record in 2013, and set a pretty good pace really for the vehicle. The example on the left-hand side, completely different again. You should think about you need safe transportation for newborn and infant babies, especially when you're moving them between hospitals in an ambulance. In the past, that's been quite a challenge for hospitals to have a safe, portable environment. But the application of carbon fibre, analysis, crash testing into this type of structure enabled us to design this pod to allow the safe transportation of babies. We've now taken that into production, and we make them, actually make the carbon fibre pods in our composite shop beside the F1 pod, beside the F1 chassis. The one on the right is different again. It's not so much new technology, it's looking at something that happened in the past and actually making it better, because it's quite a big market for this. We were approached by Californian company Singer to help re-engineer 1980s Porsche, bring it up to a very modern standard, make it very dynamic, make it very lightweight. We've got the carb weight down to 990 kilograms by the extensive use of titaniums, aluminiums, carbon fibre in it. We redesigned their 500 horse, the air-cooled engine in it. I don't think there's many people casting air-cooled engines these days. It was a great job to do. It'll be heading into production soon, and we should build around about 70, 75 of them. Now, a lot of these examples have been based on customer programs. What we wanted to do was to have a little look at what we had from a technology point of view and actually make something that we could demonstrate that technology. Now, whether or not we would sell this electric vehicle platform in this format or not is debatable, but what we wanted to do was to develop some of the lightweighting technologies, some of the battery technologies, and some of the motor technologies that we had onto one vehicle to give effectively to say, right, we have this, this is it, you can see everything now. What we had with this was brought an element of innovation into it to develop a lightweight electric vehicle platform. We integrated the cooling system into the side sills. So instead of having radiators at the front, we drew the cold air from the front of the car in the high pressure area down through the side sills, through an intercooler system, and then exit it at the low pressure area through the diffuser at the back. We get the advantage of that, we get the structural rigidity, and we also get the side impact protection, all wrapped up in the radiator system. Quite a clever use of combining structures in multiple uses. We also developed systems for making carbon fibre wishbones, which you probably don't want to hear from the casting industry, but developed carbon fibre wishbones to be lightweight, but also low cost as well. Now, in this application, it has 3 electric motors putting out around about 480 kilowatts, so about 650 odd horsepower. The plan is that we used a number of off-the-shelf parts. So the motors are off-the-shelf from YASA, transmission from Extrac, charging system is off-the-shelf, the inverters come from CASTcon. So it's something that can easily be taken into production if need be. You can also see on here the subframe system for it is a combination of aluminium lugs, could be cast or fabricated, with carbon fibre tubes. So you can expand or contract the size of it on the powertrain that you want to put in it. You can see the combination here of the air intakes at the front with the crash cans or the front impact from crash protection system. So the end result of this was it developed a chassis that weighs 955 kilograms. That would give a vehicle weight of about 1750 kilograms. Most electric cars that you see are around about 2.5 tons. So they're pretty heavy, so quite significant weight savings within this. I touched on the wishbones. What we wanted to do, we knew we had a lot of expertise in carbon fibre composites. But that's not really much use to other industries because how we use it in Formula One is not cost effective, it is expensive and it's time consuming to make. So we set a team off with a task a while ago to say, right, we want to take carbon fibre composites into more volume manufacture. How do we do that? This was the first example that they did, which is a linking piece. So we've used an example of a wishbone. The only piece of expensive carbon fibre on it is actually to constrain the outer edges of it. All the other material is recycled, either carbon fibre or glass fibre. It's made through a resin injection system, through a press system. You can embed metallic parts in it for bushes. You can also embed sensors in it as well. So if you have a crash or if the part is damaged, you know how far it's damaged. If it has a high excessive load, you know if it's been damaged in service. Now, through one press, you can make somewhere in the region of about 500,000 units per year. So very fast throughput, very fast turnaround. We also wanted to develop a method of making basically battery boxes so that we could use the battery box as a structural part of the chassis. Now, to make a carbon fibre box, you have to lay it up in a mould, put it through an autoclave normally, quite time consuming, not cost effective at all. If you could use that by a combination of pressed composites, so you have effectively a flat form, you press it and then have a form that you would have like a cardboard box, and fold it would be ideal. So we developed a system that we go through the first cure level, but leave a hinge system in place, so that although 99% of the structure is rigid cured carbon fibre, you still have these hinge elements. If you start to take that a stage further, you start to think about the opportunities of what you could actually do with vehicles or pods in the future. It enables you to then build the electronics, the seating, other aspects into a structure, then bond it in a secondary operation. So really, I hope that's given you a bit of an insight as to what we do. I think in summary, We in motorsport, I think we have a level of technology and expertise that we can apply into other sectors. We know that there's technology gaps in some of the areas that we work in, but we're pretty agile in how we go about that. Low volume production does demand structure and process in the same way that high volume production does. There's no getting away from that. But we also need to have that flexibility and adaptability within the engineering environment that we have in motorsport and take that into other areas. So really, the key for us is taking the low volume, taking into low volume is creating the discipline and focus necessary without burdening it with the costs that you normally see in systems and processes of high volume, and trying to bridge that gap. Thank you.